Now comes one of the most important parts of the tutorial, switching to unsteady flow with curvature correction. Inclusion of curvature correction improves the turbulence model accuracy for strongly swirling flow like this, but once you enable it, a steady solution is no longer enough for proper convergence. That is why the case is first run in steady mode, and only then converted to unsteady mode. So go back to the physics continuum and modify the model selection. Deactivate steady. Activate implicit unsteady. Then under the SST Minter K omega model, switch curvature correction to on. Now adjust the solver settings. Set the implicit unsteady time step to 5.0 times 10 to the minus 4 seconds. Set the velocity under relaxation factor to 0.9. Set the pressure under relaxation factor to 0.4. Then update the stopping criteria. Deactivate maximum steps. Set maximum inner iterations to 8. And set maximum physical time to 0.5 seconds. Finally, under the solution history update settings, change the trigger to time step. Now run the solver again. Because the time step is small and each time step uses 8 inner iterations, this second run effectively corresponds to another 8,000 iterations. When it is finished, save the simulation again so the history file is complete. Now create a side-by-side comparison between the original steady solution and the final unsteady solution. Start by creating a recorded solution view from the saved solution history. We will configure the setup manually, so in the popped-up window, select No. Then go to Solution Views, select Cyclone Flow Solution, and set the state name to Steady. After that, go to Scenes, then Scalar Scene 1, then Scalar 1, then Color Bar. Set the orientation to vertical, and set the position to 0.2 and 0.6. Now right-click Scalar Scene 1 and choose Copy. Then right-click the Scenes node and choose Paste. Rename the copied scene to Steady Solution. Next, right-click Steady Solution and apply the representation Cyclone Flow Solution. Then multi-select Steady Solution and Scalar Scene 1. Right-click and choose Linked View. After that, go to Layout Views, create a new layout with one left, one right, and drag Steady Solution into the left panel. Then drag Scalar Scene 1 into the right panel. Now you can compare the two results side by side. The steady solution is shown on the left, and the final unsteady solution is shown on the right. Once curvature correction is activated, the swirling core through the center of the cyclone becomes sharper and more clearly defined. Finally, let's create a streamlined scene so the flow pattern inside the cyclone can be visualized more clearly. Create a new geometry scene and rename it Streamlines. Then go back to the simulation tree and create a new streamline derived part. Use the main body and outlet pipe regions as the input parts. Use the inlet boundary as the seed part. Set part U resolution to 2 and V resolution to 8. Create a new streamline displayer and close the dialog. Now adjust the scene appearance. Set the Cyclone surface opacity to 0.3 so we can see through the geometry more easily. Set the streamline display mode to ribbons. Then set the streamline scalar field to velocity magnitude in the lab reference frame. To animate the streamlines, set the animation mode to tracers. Set the delay between tracers to 6 seconds. Set the head size to 0.01 and set the tail length to 1 second. Then go to the Streamline Integrator settings and set maximum propagation to 15 so the ribbons extend all the way through the fluid domain toward the outlet. At that point, you can press play in the animation toolbar to watch the flow develop visually and stop it whenever you like. And with that, this Cyclone Separator anisotropic flow setup is complete. We started from the Cyclone geometry, created the fluid regions, built the volume mesh with targeted refinements, selected the turbulence and flow models, defined the inlet conditions, prepared a scalar pressure scene, ran a steady initialization, switched to unsteady with curvature correction, compared the two solution states, and finally created animated streamlines to visualize the internal swirling motion. So this chapter gives us a really solid CFD workflow for Cyclone Flow and STAR-CCM+, and more importantly, it shows why the modeling details matter. The combination of mesh refinement, the K-omega SST model, and curvature correction has a very visible effect on the predicted swirling core inside the separator. Thanks for watching, and I'll see you in the next video.